Now in this video, we're going to look at one example on a Poisson process. So here it says customers arrive to a bank. So right there, you see that's the arrival process. According to a Poisson process, having a constant average rate of 8.6 customers per hour. So this average rate is the key parameter of any Poisson process. It's the lambda. In this case is 8.6 customers per hour. So then you have to pay attention to the unit of measure every time, because sometimes the lambda is given in terms of hour, and then the question is asking you to calculate some probability in terms of minutes. So you have to do that conversion. Suppose we begin observing the bank at some point in time. What is, part A, what is the expected value of the number of customers that arrive in the first 30 minutes? Well, here, right there, you see that it's asking you in terms of minutes. Also, it's asking you about the expected value. So expected value, we had the formula right here. It's just lambda t. But what is the random variable that we're going to calculate the expected value for? Right? That's the first step. So you know that the random variable of type Poisson is n of t. And in this case, it looks like our t is 30 minutes. If we want to keep everything in terms of hours, because lambda is given in terms of hours, this is going to be n of 0.5, right? Because 30 minutes is 0.5 hours. So n of 0.5 is a random variable, and what we're going to do here is to calculate the expected value. Expected value of n 0.5. We know that that is equal to lambda t. Lambda is 8.6 customers per hour, and the t is 0.5. So the expected value is 4.3 customers. 4.3 customers arrival is the average of number of customers that coming in half an hour. Part B, what is the probability that 3 customers arrive in the first 30 minutes? So the random variable doesn't change. Still is t is 30 minutes. So your random variable is n of half an hour still. But what you're doing here in part B is calculating a probability. Probability that n of 0.5 is equal to 3. So how do we do that? If we go 2 slides back, this is how you calculate probability. Probability of, right there, we're calculating n of 0.5 equals to 3. So let's use that formula to calculate the probability. Is going to be e to negative alpha, alpha to x over x factorial. In this case, our alpha, as you know, is equal to lambda t, which is 8.6 times 0.5, so 4.3. So it's going to be e to negative 4.3, 4.32x. And here's your x. You're calculating that your random variables, what is the probability that your random variable is equal to 3? So 3 over 3 factorial. And if you do the math here, you're going to get 0.18, which means there's 18% chance that 3 customers arrive in the first 30 minutes, given that the arrival process is a Poisson process. Part C says, what is the probability that 5 or fewer customers arrive in the first 30 minutes? Again, the random variable is still n of 0.5 because t doesn't change. But you're asked to calculate 5 or fewer. That means n of 0.5 less than or equal to 5, right? 5 or fewer. Well, that is probability of n 0.5 less than or equal to 5. Am I right? Yes. Well, that is a CDF, right? Basically, you're calculating n of 0.5 less than or equal to 5. So you would have to sum from 0 to 5 over the PMF function. So what has to be done is a summation from 0 to 5 over that formula, over that PMF, e to negative 4.3, 4.32 j over j factorial. Essentially what you're doing here is that you're saying I'm going to add probability that n 0.5 is equal to 5 plus n 0.5 is equal to 4 all the way to n 0.5 is equal to 0. And if you want to do this by hand, you would have to calculate each one of these separately, just like what we did in part B, and add them together. And if you do that, you're going to get 0.737. 73% chance that you will see 5 or fewer customers arrive to the bank in the first 30 minutes. So that was the example that we wanted to go over here.